Okay, so I've given you guys all back your input modeling reports, so you should have feedback on that. If you have any questions, please let me know. I tried to provide, I think pretty much all the input modeling reports look pretty good. The only major things that I would bring up was things like whether it was complex enough, like if it was like, well, we just sort of modeled that there's going to be an arrival process and a service process, and we just want to see what happens if we make the service process faster. Like, well, we kind of know what's going to happen there, so that we don't really have to simulate that. But so it'd be like, well, are you going to maybe come up with a sort of an innovative queuing scheme that it's not clear whether it'll be better or worse, and then how are you going to simulate that queuing scheme? That's kind of a much more sort of complex thing. Are you going to change maybe the schedule for the service capacity in a particular way where it's not clear whether you should schedule more at sometimes a day or more at others? That's something that that sort of suggests that, well, maybe simulation would be good to do that. So like ultimately, I think it was great. Like you guys have all demonstrated that you have access to systems, you can get the data, you've got a well-motivated system. But then the question will be moving forward for your project is then, can I find a problem that I don't already know the answer to simulate? It doesn't have to be too complex. I mean, I'm not expecting to build a semester's worth of work. I mean, it's only have a couple weeks to work on it, but I still want something where before, like when you're presenting it in your final project presentation, your 10-minute presentation, that at the start of it, there's multiple ways the results could go. And your presentation then brings resolution to, but here is the result that ended up actually being the case. If it's just validating something we already knew to be true from back of the envelope calculations from 470 or something like that, then it's not, that's not really what simulation's for. So that's kind of the only sort of feedback I have here. So I did, that feedback has been returned there. So I'm going to leave you alone for the final report. And the next thing is this presentation video and final report and these peer reviews. I've never used Peerceptive before, but that's what I'm going to use this semester. So I'm setting up that assignment. So it'll be collected a little differently than it has been. So there's some of the current places where you turn in the report and the presentation, and then where you sort of get scored for your peer reviews are going to disappear and be replaced with a Peerceptive assignment, as I sort of feel confident that I've set it up correctly. So, but that you won't have to worry about until the last week of class. So it won't change how you do any of your prep. It's just how we collect that. Then lab schedule, only two more labs, labs 9 and 10, output analyzer, which is relevant to the stuff we're going to be talking about in this unit. And then advanced topics. So just more things that you can do in Arena that might help you modeling more complex things in these systems. And then otherwise, we've got open labs for this modeling help. So the TA you can sort of have time to work together there to get your more advanced questions answered and so on. Otherwise, they were winding down on the last couple of ICAs here. Their homework H is out, and the final homework will be assigned next lecture. So it'll be kind of made available next lecture. Homework J2. This is the one homework that that cannot be dropped. All the other homeworks is a drop one policy. There won't be a solution set as well because we collect ABET metrics from it. So there needs to be some consistency. And yeah, so any questions about the admin? Uh-huh. Sure. Actually, it's voting day. No clicker questions today. If anybody needs to, if you want to vote, if you want to go prep for 470, everybody gets an excused for today. I was late anyway, and I feel bad about that. Um, last time we kind of talked about hypothesis testing, so I'm just going to skip through this and only might kind of stick on some of the newer stuff. We talked about the t-test and where it came from. It says this pivotal quantity, and I kind of hinted at this distance thing that this is, if you have the t-test is what we call a parametric test. So what it's sort of assuming is that your data are normally distributed, and it's trying to say, do your if we take for granted that your data are normally distributed, we don't know the mean of your data. We don't know the mean, the population mean, the true mean of your data. We know the sample mean of these samples. But given these samples, then what we're trying to evaluate if these samples came from a normal distribution with a hypothetical mean. So our hypothesis is purely about the parameter of the normal distribution, the mean. So that's why it's called a parametric test. And so we have a null hypothesis that we're testing against, mu0, and then we might have your data might have actually came from an alternate hypothesis. Again, the assumption is the alternate hypothesis is a normal distribution with the same spread as the real distribution, but just a different mean. So that's all the t-test is testing, is whether there's a difference in means. And so if in the real world, the difference in the hypothetical mean, mu0, and the real mean is this quantity, it's absolute value here. And the way that shows up in the t-test is after you go through this t-test statistic, if I go with this thing here, then that's going to turn your sample mean that you took of your data into a point on this so-called pivotal quantity, this, say, blue curve, if the null hypothesis is true. And if the null hypothesis isn't true, if it's actually coming from a distribution with a different mean, it will come from this red curve. And so this distance in t space, so t statistics distance here, reflects this scaled distance here. So in the real world, the means are separated by the numerator here, but in this pivotal quantity, the width of these distributions doesn't change, but the spacing between them changes as you change like the number of samples. And so what we do when we take more samples is we move these two curves farther apart. So the idea here, if I go back to this original one, is this blue curve are all of the t statistics I would get if mu0 was the actual mean. This red curve is, let's say it's the actual distribution. And so I get a t statistic out that's just it's just along this horizontal axis. And I set this vertical line, this threshold, based on the blue curve. And I'd say that I'm willing to believe that it came from the hypothetical mean if it is to this direction, so to the left of this vertical bar. But if it's to the right of it, it's very unlikely it came from this blue, and so it probably came from the red. But you can see there's so much overlap between the red and the blue here that if I just make a decision based on this threshold, there's going to be a lot of points generated by the red that are going to be concluded are actually from the blue. So when I sample more in T space, it moves the red over. It keeps the blue in one spot, but it moves the red over. So the real difference in real life gets separated in T space due to the extra samples because we've squashed some of that variation, so it gets spread out. So now if I use that threshold, then it's a much better discriminator between the red and the blue curve. And if I sample more and more, it gets better and better. Is the kind of idea there. But there's the alternative that I can do, which you saw in the second half of homework H, is that you can just decrease the variance. So, because, well, how am I going to decrease the variance? If you engineer your your experiment so that you can, for example, pair samples together, like we're going to remind you that how you did in your homework, that removes variance, because if there's common sources of variance between the two groups that you're comparing, it factors them out. It controls for that. The word control in statistics just means account for variance. So controlling for variance means getting rid of it or accounting for it. And so by accounting for variance, that provides another way to separate these things out. So I can have so back here, I had 30 samples and a variance of 2, standard deviation of 2. Here I have 30 samples and I've managed to reduce my standard deviation to 1.5, and that also moved that out. So, that, how do you do that? This is, again, what we do in the second part of your homework. If you were to, for example, take the same input data and feed it into your real simulation, as well as the data were from the real world. So it actually ran through the real world, but we took the input data from the real world and piped it through the simulation. That removes a source of variance, because if we just simulated the simulation with random data, then now we've got random customers. So now we've got a difference in customers. So that adds a source of variance to the variance in our output. We'd say, okay, we're going to control for variability in customers by just putting the same customers through both the real system and the simulated system. And that controlling for variance is going to reduce the variance in the differences between the outputs. And that is going to give us more statistical power. So that's why this one sample t-test is used in this particular case, because we're going to say, for these customers, we ran it through two systems. We got one performance metric. We take a difference in that one performance metric, and then we generate a bunch of those differences from a bunch of different sets of customers. And then we look at those differences and we compare them to zero using a one sample t-test. And that's going to give us much more power than if we were to do a two sample t-test where we've got independent customers in the real world and independent customers in our simulation. So that's why we do this pairing. It's to reduce variance. And we're going to talk a lot more about that in an upcoming unit. But that's what's going on in your homework. That's where this thing, why am I piping real data through? It actually has some utility to do that. So you've got your simulated data, which is from real customers. You've got the real data, which is from the real world. You calculate differences. From those differences, you get a mean difference and you get a variance on that difference. And then from there, you can say that, you can say, well, what is my hypothesis? Well, my hypothesis that I'm potentially rejecting is that these two systems are the same, that I've built a good representation of the real world. That's my null hypothesis. If my simulation is a bad representation of the real world, I want to detect that. So detecting a difference from the null, in this case, is detecting that my simulation is a bad representation of reality. So that's what I've set up here. And then I ask you to do a power analysis in the homework. And what that basically means is that I'm going to say, if my real world system is close enough to my simulation system, I'm willing to accept the simulation system as not being perfect. I know my simulation system can't be perfect, but I just want to get it close enough. What is close enough? Well, somebody needs to tell you that. And so in the homework, it does tell you, it says they have to be off by a certain amount of whatever unit they're, so 2.5 jobs if they're simulating jobs or something like that. So in this case, you're given a difference between the real and the simulated that you're willing to tolerate. It's like anything less than that difference, we're calling these two populations the same. And then we scale it by the standard deviation that we measure in the simulation. And that gives us a scaled version of the difference that we're going to call an effect size. And so for that effect size and a given false positive rate and a given statistical power, we can calculate how many samples we need in order to guarantee that we can detect anything bigger than that detect size. Smaller than that detect size, it's all going to get washed out in the noise. But bigger, then with 80% probability, we'll get it. So, and that's what those operating characteristic curves are in the back of the book. So in that homework, you're going to flip to this one. You're going to take the effect size that you calculated down here. You're going to flip the statistical power into the false negative rate, beta. And so that's going to be 20% because that's just the convention. And so you're going to slide along here until you hit your effect size. And then for whatever effect size that is, you're going to look at which curve it best corresponds to. And you'll be able to then say, okay, I need at least this many samples in order to reach that statistical power. That's a power analysis. So any questions about the power analysis that you have to do for the second part of the homework? Pretty clear. The alternatives you can use a power analysis for is if somebody already designs an experiment with 20 samples or whatever, then you can go back and say, okay, here is the statistical power that you have given the variability in the system. You know, that's so you can do it in multiple ways. And if you look into MATLAB, R, SPSS, anything G-Power, anything that does a power analysis, it will give you options. It'll say, do you want me to calculate the number of samples? Or it'll say, no, 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 I already know the number of samples. I want you to tell me the power. And so, you know, you can, the numerical tools that are out there automatically do that for you. But we're having you do it by hand this first time. Okay. So, yeah, I just said that that's a parametric test, meaning all we're focusing on is the parameter of the distribution. If you don't know that your data are normally distributed, then you have to go to a non-parametric test. And so you won't have to do this in this class, but in general, whenever you're handed data and you're trying to test, are these means different? Are these distributions different? You really need to say, are these normally distributed? If they aren't, is there something I can do to them? So it's common to run them through a transformation to then make them normally distributed. Like maybe you run them through a logarithm, and maybe the logarithm of the data are normally distributed. That will often be the case. There's other things you could do, and then if that transformation is normally distributed, then you can do the test there. If that's just not possible, then you have to find a non-parametric test, which can be used on a more generic data set. The downside here is you lose power, you lose sensitivity, but you can use it on, you know, any data. And then there are you know, exact non-parametric methods that make no other simplifying assumptions. So I bring that up because the chi-squared test, for example, doesn't make any assumptions on the shape of the data exactly, but it does make an assumption that the expected value in each bin is 5 or greater. And there are other tests like Kolmogorov-Smirnov that do not make those assumptions. So a KS test can sort of always be used as long as a parameter is not being estimated. But a chi-squared test, you aren't worried about whether your data are normally distributed, but you are worried about whether you have enough data to do the chi-squared test. So there's all these sort of categories of when you're allowed to use a test and when you're not allowed to use the test. In this class, for reasons that will justify in the units that we're starting, it will almost always be safe to use good old t-tests, paired t-tests, ANOVAs. But as you get out of this class and do more stats, you really do need to say, am I using the right test for these data? So we talked about where chi-squared stuff comes from. So this is sort of, I mentioned it's, if you talked about a binomial test, if you know, chi-squared's all about counts. So if I have 10 bins, I could simplify that to saying I have 1 bin and 9 other bins. So what's the count of data I get in 1 bin versus not in the bin? And that's a binomial distribution. And so this is like the distribution, the number of observations landing in a class. Well, if the expected value here is 5.5 of binomial distribution in P, so I'm saying that if I have 100 coins that I flipped and they have a 5.5% chance of coming up heads, then this is the distribution of heads I'd expect to see. I'd expect to see of those 100, around 5, sometimes less than 5, sometimes more than 5. And so you could imagine that this would be, you know, 1 bin out of many. And if it wasn't in this bin, it'd be in one of those others. But if I'm just focusing on this bin, it's just a binomial test in or out. And so if I consider different probabilities, I could say, well, like up here, this is 100 coins where my probability of coming up heads is such that I get an average of 1 coming up heads. Well, sometimes I get 2 or 3, but notice that this isn't very much bell-shaped. It gets truncated here on the left. If I go to an average of 2 out of 100 coming up heads, well, that also gets kind of truncated over here. It isn't until I get to about 5 that this binomial distribution looks nice, symmetric, bell-shaped with not a lot of truncation here on the left. So, and then once I get up to 6, this looks pretty normal. And so that right there, that transition from going from truncated, not really that bell-shaped and normal, to bell-shaped and normal, that is the approximation that makes the chi-squared test go. That's why you can't use a chi-squared test if the expected number falling into bin is less than 5, is 4, 3, 2, 1, because none of these binomials look like a bell-shaped curve. So that's where that comes from. And that's why it's so, so, so important that you make sure that your expected count in every bin is 5 or more. And what do you get for that? Well, if your expected count is greater than 5 or more, you can approximate the distribution falling into a bin as a normal distribution. So the normal distribution, that's going to mean that if you subtract off the average and divide by the standard deviation of that approximation, then you get a standard normal. So this chi value here is just a z-score. And that's cool because then if I square it, then this ugly formula here with the square root in the bottom there turns into something that I can use a partial fraction expansion on to create your chi-squared statistic. So here's the observed count, here's the expected count, here's the expected count, there's the square. In the second bin, here's the observed count, here's the expected count, here's the square, here's the expected count. That is the chi-squared statistic, which is just the partial fraction expansion of the z-score that you got from this approximation. And so this is why 2 bins gives you 1 degree of freedom. So for every number of bins you have, you already know the sort of the other bin. And so this is sort of saying that the sum of this chi-squared, even though you're adding up 2 things, it's got 2 terms, it's basically going to follow the distribution of a squared normal. So that's the beauty of a chi-squared, is that it's the sum of squared normals, but it's 1 less squared normal than the number of bins. So like up here, I've got the number of degrees of freedom here. So the yellow curve here, that says a degree of freedom of 1. That means that I have 2 bins. So my chi-squared's got 2 terms, but that is going to be approximated as 1 standard normal squared. And so that's why you get this ski slope. If you take a standard normal and square it, all of its values become positive, and then you get this distribution. And as that goes up further and further, so here if I had 10 bins, that's the sum of 9 squared normals. And that's why you get this sort of hump-shaped thing. So that's how a chi-squared test works. That chi-squared statistic comes from just squaring normals and adding them together. That's how you generate that table. You can generate that table by yourself just with a normal distribution. But the only way you can get that table is if the expected count in every bin is 5 or more. So that's where that comes from. And that's all I'm sort of saying there. And so this is an example where if I've got a true distribution that I'm testing for, and I've got a very similar distribution and I calculate chi-squared values for it, and then I bin those, then I get this. If I have a very different distribution and I generate chi-squared values for it, I get this lump. And you can see that as these curves as the distribution gets very much more different than my null, then these distributions get very different than this chi-squared distribution up here. And then I end up basically doing the same thing I did with my t-test, where I set a threshold, and anything to the right of the threshold is rejected, anything to the left of the threshold is not. So that's why large values of chi-squared are going to correspond to low p-values. Small values of chi-squared are going to correspond to high p-values. And that is the mechanics behind the chi-squared. All right. So any questions about that, about why, so I'm just trying to motivate so that it's burned into your brain why 5 is important for chi-squared. If you don't have 5, then there are other tests that are more modern, like the G test is like a chi-squared test where it's more like 3 is the limit. There are also so-called exact tests that don't make approximations, like the binomial test and Fisher's exact test. And so these work really well if you have small expected values and you need to use something like a chi-squared test. So these are things, again, outside the scope of this class, but I don't want you to think that the chi-squared is the be-all and end-all. It's a great tool, but there are more modern tools. There are tools that if you can use, you should use. But if you just need something and you don't have a chance to sort of figure out what's the best tool to use, then the chi-squared is a good first one to go to. And then the KS is another example where if you have small amounts of data, then we can use this K-test. The KS test is an exact test. If you're wondering where the statistics come from for an exact test, it's a little more exotic. So the idea behind the KS test is you have a hypothetical CDF, the red curve, and then you have your data, which you've sorted and plotted, so you get an empirical CDF, and you look for the difference there. Well, then the question would be, how do I figure out what's a big enough difference for me to call it not, close enough to my CDF? Like, how do I set up that threshold? And so for the KS test, they said, well, imagine that you do a so-called drunken walk where you know that you need to start at 0 and you need to end at 1. And so imagine if you were walking from left to right and you just randomly took steps up and down, but those steps were, this is out of all of the types of ways you could walk along this path or walk near this path so that you were guaranteed to end up here. If you look over all of those paths, then you get what's called a Brownian bridge. And so this is an example here where I flattened it out, where you start at 0 and you end at 0. And so this walker walks to the left, to the right, to the right, to the right, to the right, to the left, and so on. So this drunken walker is walking around randomly, but the drunken walker has to get back home. So if we consider all of the ways a drunken walker can start at a point and get back to that point, and then we look at how far away the walker gets from the flat line here, that gives us the distribution that's used for the KS test. So it makes 0 assumptions about the shape of the data, but it uses this as a model of error. And it's saying that, if you're farther away than a drunken walker could get and still make its way home, you're probably not that distribution. That's where those statistics come from. So the more assumptions we make, the more enriched the statistical tool we can build, like the t-test or the chi-squared test, and then in this case, no assumptions. And so that's where you get the power. We have, and so you get more freedom with fewer assumptions, but sometimes you get more power with more assumptions. And so there's sort of all these trade-offs that are made when you build these tests. And that's why we have all of these different tests, like the Anderson-Darling is yet another alternative to the chi-squared and the KS. And then and that's, it's a very powerful test. But it compromises some flexibility. So there's Shapiro-Wilk. That's the one that you use much more often when you leave a class like this one, because in order for you to use the t-test, the ANOVA, the paired t-test, you have to do a test for normality before you can even use any of those parametric tests. And this is, one of the leading tests for normality. It doesn't do anything else, but because it's just designed to test for normality, it does that really, really well. So again, I'm not asking you to do a Shapiro-Wilk, but the little things you do in this class, if you leave this class and try to do them in a professional setting, then people will start wondering why you didn't do these things. And so these other things are things you should know exist, because if you go down a data science pathway or an experimental pathway, eventually you will have to do these additional tests to even give you license to do the tests that you do in this class. Okay. So yeah, we've been doing the thing that I had to skip over last time that I want to at least highlight is when you're doing you build your model and you run it, then you're going to generate lots of different outputs. You've seen this in experiments here. So you might say, I have a simulated utilization, a simulated delay, a simulated line length. So the question here is, which one do you test for a difference? So I said, I've gone into my final project, I've changed my queuing system, and so my queuing system is very different in one situation than another. I want to see which queuing system's better, so I'm now going to maybe study average delay, but maybe I also want to study utilization. So do I look for a difference in utilization? Do I look for a difference in delay? Do I look for a difference in all of them? Does anyone have a guess as to what could be wrong with looking for a difference across multiple output variables simultaneously? Does anyone know if heard the term phishing in statistics? So what's the chance of detecting a difference wrong in one measure here? What do we call that? So there's what is the term or the variable or the number we commonly use. I'm going to do a test. I want to say, I want to test to see are my two systems, simulation and real, do they have a different utilization? So I run a test, a statistical test, and it says, yes, there's a difference between these, but that sometimes is wrong. So what do we call that type of error? False positives. That's right. It's false positives. So what is our typical false positive rate for our tests? What number do we use typically? 5%, right. So I have a 5% chance of incorrectly saying that the difference I see in utilization is real. I have a 5% chance saying that there's a difference in delay that's real. I have a 5% chance detecting a difference in maximum line length when there actually isn't one there. So I keep having if I have a bunch of these outputs that I'm measuring, each individual one, there's only a 5% chance I'm going to incorrectly say I detected a difference. But those 5% add up. So you might say like, oh, they're the same utilization, same delay, same line length. Oh, but they're a different, I don't know, whatever, some other output metric here, a throughput. And say, I finally detected the difference. Well, this is like, you could test for, blue M&Ms versus green M&Ms. You could test people for all sorts of populations that eat blue M&Ms, populations green M&Ms, look for differences, but eventually you will find a difference. But just because you find there's a slightly higher cancer risk in the green M&Ms case doesn't mean that you actually found a cause for cancer. So this is what we call the multiple comparisons problem. And so what we have to do is when you're doing multiple comparisons, you have to correct for it. And there are more sophisticated ways to do it, but the simplest way that we do in this class is something called Bonferroni correction. And the idea here is that if you look at what's the probability of getting at least one false positive? Well, that's basically 1 minus the probability of no false positives, which is 1 minus alpha to the k, where k is my number of comparisons that I made. So as alpha is basically as k gets large, then this probability definitely gets larger than alpha. It inflates my what they call family-wise false positive rate. So in order to make it so that if I've got multiple comparisons, so in that last one, this would be 3 comparisons. I'm comparing the systems in 3 different ways. In order for me to guarantee that across that 3 comparison test, I'm getting a 5%, then what I'm going to do is for each individual test, I'm going to divide their alpha by 3. So in order to get a 0.05 alpha at the family level, I need a 0.05 divided by 3 alpha at each individual comparison. That's how I prevent phishing. That's going to mean it's going to be much harder to find differences for each of these individual metrics, but it's compensated by that I'm looking for differences in multiple things so that when I look across all of the things that I'm looking across, then there's only a 5% chance that I'll accidentally find a family-wise error. That's what we mean by Bonferroni correction. It is named after somebody named Bonferroni. So does that make sense? Is like if you're comparing multiple outputs, if you compare them all with a 0.05 error rate, then the error rate for the whole process of comparing multiple will be much, much higher than 0.05. You're going to inflate your false positive rate because you're going to end up phishing. You're going to get, it'll be a higher chance that you'll just find one of those will show a difference just by a mistake, and you'll amplify that mistake. Okay, so that's what we mean by Bonferroni correction. We'll see that again. But this 0.05, and I mentioned this last time, In engineering, if you're in an R&D laboratory and you do this stat stuff, if the next step is to dump more money into a potential new solution, a potential new market, a new technique, sometimes you're okay with an inflated error rate. And this is one reason why a lot of engineering textbooks don't even worry about this Bonferroni correction, because they assume that that once you get, do this experiment, if you happen to find that one of these, triggers and says, oh, there's a potential difference between these two cases, this queuing system and this queuing system, then there will be money and resources to follow up with more tests of that fancy queuing system. So it's almost okay that you might accidentally detect a difference that's not there, because they're much more worried about missing important differences than finding too many, because they're going to follow up and verify if that is a real difference. So although scientifically it may be important to do this Bonferroni correction so to keep you honest about your error rate, so you can actually say with a straight face that you had a 5% error rate in your experiment, it may be that in your application area, you actually are willing to tolerate a much higher error rate. And so you can just go and say, oh, I've got 3 comparisons. That's not that many. I'm not even going to worry about correcting for this, because I just want to make sure I detect anything that's there. And that's something we talked about a little bit earlier. All right, so that's kind of the review of all the things that I want to make sure that we've covered to this point before we now start on point estimation, which will be a big part that'll motivate the rest of this unit. So any questions about any of that? Where the stats come from, the terminology we use? Okay. Unit J. So this is a new unit where we will be focusing on things like, what are the types of performance measures that should we base our decisions on? How do we make decisions about how long to run our sims and how much statistical power we need? And how also do we make decisions about how long we run our sims and how much so-called bias that we want to remove from our estimators? So before we can get to all that, we have to talk about there's 2 types of systems that will simulate, and thus 2 types of sims that go along with that: terminating and non-terminating. So and I'll talk about each one of these, but a terminating sim is going to correspond to a transient simulation. A non-terminating system is going to correspond to a steady state simulation. A lot of people just swap these terms, and that's usually fine. Just formally, the systems use these 2 terms, terminating and non-terminating. And then the sims you use to represent those systems use these 2 terms, transient and steady state. Transient goes with terminating, steady state goes non-terminating. It's fine if you sometimes swap them, but as long as you're keeping them both on the right side. So what do we mean by these 2 things? So a terminating system is a system that runs until a real end event that actually exists in the real system. A terminating system is like a bank that opens every day at 8 a.m. and closes every day at 5 p.m. And that 5 p.m. is a real time. So when you're simulating the whole system, you simulate the opening event and the closing event. It has a finite duration in real life. So this could be a fixed length of time, but also could be a random variable. It might be that you know that you close, like maybe the bank closes at 5, or it might close when the last customer is served. So maybe the bank sometimes stays open a little bit later, but they close their doors at 5, and then they stay, they process individuals who are in the line. And once the line is empty, then they close. Well, in that case, the time that they end is random, but still they end. That's the key point. A terminating system is a system where it is important that we model that they stop at a particular real time. And so we simulate a terminating system by a so-called transient simulation. So we call it a transient simulation because if a system ends, it also starts, and we care about the start time. So like if you have a Walmart that's open 24/7, that is not a terminating system. And we don't ever worry about transients. Now, if that Walmart happens to one day close for repairs, a storm, whatever, when they reopen, it won't be business as usual the time when they reopen. There are transients that have to die out as people come back to the Walmart, they'll open the doors, they do all the things that they normally don't have to do. Likewise, for a bank, every morning when they open up at 8 a.m., there might be people waiting outside the bank. They need to deposit checks or talk to a teller or whatever, and they're just lined up there. It is not the normal arrival rate when you open a bank up because there could just be people waiting there. Now, after about an hour, then it goes back to kind of at that point, people arrive, they go in, like there wasn't a queue that's waiting for that. So there is a transient that is important in the bank case that that you like of those people that you just have to deal with that have been waiting outside the door. In the Walmart situation, which I'll get to in a second, if I to run a simulation of a 24/7 Walmart, my sim has to start and it will have transients, but the real world system won't have transients. And so that's the key difference here is that this is a type of system where we want the transients. They're not an artifact of simulation. They're something that are important for us to take performance measures over. So that's this type of system. The other type of system that I'm about to introduce is that we need to throw those away because they're just an artifact of having to start the simulation at some time. So that's how you get the bank. This is a great example of a terminating system that is simulated by a transient simulation. All right, any questions about what I mean by terminating versus transient? It might be easier to see if I contrast that with a non-terminating system in just a second here. But in Arena, in the run setup, and now this is in the ribbon, but this is in the replication parameters, you have the option to set the number of hours per day, and you can set how long each replication goes. So in this case, we set a terminating condition here where I said that the time in the sim is greater than 600 seconds, or the Q is equal to zero, or sorry, and the Q is equal to zero. So this call center simulation here, it runs, it closes down at the end of the day. It closes down either when we hit whatever 5 o'clock and when no one else is left on the phone line. If there's somebody on the phone line, they'll close a little later. If nobody's on the phone line right at 5 o'clock, they'll close immediately. So, but the point is, they terminate, the sim stops. That is the end of the day right there. That is a terminating condition. And that is an important thing that we need to simulate for this system. We don't just arbitrarily stop it while there are people in the phone queue. So here we have to actually wait for those people in the phone queue to get rid of them. And then that's when we stop the system. All right, so that's terminating. Contrast that with non-terminating system, it runs for a relatively long period of time, practically infinite. So we studied here the steady state properties of the system. No one does operations research about how to optimize the opening of a Walmart of a 24/7 Walmart, because it happens so rarely. All you really care about in a 24/7 operation is the steady state behavior. What happens after you've opened them? In a bank, you really do care about how do we deal with the 8 a.m. rush and how do we deal with getting people out by 5 p.m. You really care about that there. For a non-terminating system, you don't care about the endpoints, you just care about the middle. And so that's why we study the steady state properties of the system. They're not influenced by the initial conditions. So it doesn't matter how many people were in the checkout lane at the start of the system. Those things don't matter. We need to factor those out. If we have data that seems to be related to the initial conditions of our sim, we probably need to throw that data out and wait longer and longer and longer until we get data that is uncorrelated with our initial conditions of the sim, because that's the stuff that we care about in our long run system. So we study non-terminating systems with so-called steady state simulations. There are initial and final times in the computer because we can't run the computer forever, but they don't have any meaning in the real world. It's just where we arbitrarily stop the sim and gather data. So the initial condition is hopefully picked by an expert to try to reduce bias. So we try to initialize the sim like we'd say, well, in a checkout lane at a Walmart, normally there's about 10 people in line. So when we start our sim, we want to try to start it with 10 people in line to minimize artificial transients, because we want to kind of start the sim off as if it's already been running. So we ask a domain expert, or we ask somebody from 470 to say, like, what do your models predict would be kind of the steady state behavior of a queue in this Walmart? And your 470 material would say, oh, on average, there would be about 6 people in the queue. Okay, well, then I'm going to initialize my sim with 6 people in the queue. And that's what I mean by is set by an analyst. And that way I don't have to wait for that steady state to be reached in the system. I can just kind of hopefully start very close to there. And then the stopping time ensures that you reach normal operating conditions. So I'm going to run steady state simulations for long time periods, not because I care about the what's going on for long time periods, but a lot of times because I want to get rid of any of those artifacts that were generated at the beginning of the simulation period. So we need to choose a long time period, and then also potentially a period of warm up where we actually discard any data in that warm up period initially, because it's tied to initial conditions which we don't care about. So choosing the stopping time and the warm-up period will be very important. So examples here are assembly lines that shut down infrequently, telephone systems that are open 24/7, hospital emergency rooms, 24-hour grocery stores, etc. These are things where we really don't care about the rare events where they stop, they close and open. We care about, how they run forever. All right, any questions about what I mean by terminating versus non-terminating, steady state versus transient? Okay, so this is kind of graphically, this is our terminating system with our transient simulation. We start the system, let's say this is number of people waiting in line at a bank. When you open the bank, nobody's waiting in line. It quickly ramps up, and then until there's a bunch of people waiting in line. All of this is stuff we care about at the bank. But at a Walmart, in our sim, it takes a while for people to enter the Walmart in our sim. But in the real world, they're already in the sim. They're already in the Walmart. So in the terminating system with our transient sim, we're going to keep all of these data. In our non-terminating or steady state, we are going to pitch these data right here because they're just an artifact of the sim. And we only care about the stuff over here, which is after the system has reached its steady state. So our question is, how big should this period be? How long should this be? Over here, our question is, these are fixed. The bank opens at 8, it closes at 5. The question here, which is also a question here, is how many replications do I run of this? So how many replications here? How many replications and how much data do I discard and how long do I run this? Those are the key things. So I'll skip that clicker question as said before. So this brings up like run real simulations here. And so there is all sorts of variability that I get out of my sims that I can manage in different ways, depending on what type of sim that I'm running. So if I just ran 3 simulation runs of this queuing node, this MG1 queue, each independent replication I could divide into 5 batches. And so these are 3 independent runs. So they all started from a different random, and it's a different random seed. And so seed 1, seed 2, seed 3. So across them, these are independent replications. So then within the sim, I can cut the sim up into so-called batches. And so it's like, in this case, I'm batching into 1,000-minute intervals here. So, and then each one of these batches can have certain amounts of variability. So we know we have independence going across here because we started them from different random number seeds. So this average, whatever we're measuring, average wait time or something like that, this is going to be independent from this one, is going to be independent from this one. A question we have is whether they're independent in this direction. And so if these batches are long enough, you can gain independence. If these batches are short enough, then the number here will predict the number here and so on. So you can kind of see that like all of these numbers are pretty low. You see that these numbers are low, but then these together get higher. So that is kind of concerning if I'm considering this to be an independent sample. So if you can show that there's independence within a replication, sometimes for a steady state simulation, you can run one replication, but cut it up and treat it like five. So by cutting up a really long run into five separate chunks, then it's like running five simulations. But that becomes problematic in a case like this, where you can kind of see that this is sort of getting larger every time, where if I know the previous value, I know the next value is going to be larger. And so that lacks that independence. So I can't chop these up into independent runs. And so this is what I'm trying to show here is that when can we count on independence and when not? Across replications, we always have independence. Within replications, we might have independence, but we generally can assume that we do not. So within replications, we have to treat different than across replications. So that's what, when we're talking about estimates, we have to ask, are we making an across replication estimate or within replication estimate, and how do we treat those different? So each one of those runs, I'm going to be calling a replication. I'm going to use R instead of N for the number of replications. Across replication data, like I said, are always independent. They're identically distributed because they came from the same model. And they're often normally distributed because they're often averages of replication data. And if you have averages of lots of numbers, that summing process, because of the central limit theorem, tends to make them normally distributed. So that's the beauty about sim, is that across replications, you automatically usually meet all of the assumptions needed for a t-test, for an ANOVA. You can do a parametric test because you generally assume that these numbers are normally distributed, they're independent from each other, and they're identically distributed because they're all from the same sim. So that's well suited for statistical tests across replication data. But then, and because of that, we can also use things like standard error. So standard error is a measure of the width of that Bell distribution that we get from taking averages. And so when you have independent observations, you can calculate a standard error, which characterizes the spread of the estimate of that average. And so in this replication here, I can say the average wait time is 3.6. The real average wait time is, I don't know what, 3.75. I don't know, but I could put a distribution around this, 3.6. I could put a distribution of possible numbers around this, and so on around this. And with that spread, I have some confidence that the real average is within that spread. So when I know that these are independent and normally distributed, then I can do the statistical test. I can also calculate the standard error, which gives me an idea of how far off that estimate might be from the real value that I'm trying to estimate. And so as I increase my number of observations, my spread is going to collapse. And so I will get more and more confidence that that point estimate is close to the real number. Now, the problem that we have is within replication data. So those data going vertically in that table, those samples may not be statistically independent, like those ones that we're constantly ramping up. So if I am to try to look across those data, like the inventory for week 1 may be correlated with the inventory for week 2, because week 1's inventory that's unused might be pushed over into week 2. So if you know you have 5 widgets left over at week 1, you might have at least 5 widgets at the start of week 2. So that autocorrelation means that if I have samples across time within a replication, I can't do statistical tests on them. I can't summarize them using standard error. There's a lot less that I can do when the samples are taken from within a replication. So that's why I don't, even though it feels like I generated data from 1,000 customers within a replication, that feels like 1,000 points of data. But we have to consider those as coupled data, because one customer's performance may predict the next customer's performance, because one customer, how long it takes one customer to get out of the system may affect the experience of the next customer and the next customer and the next customer. So even though it feels like you're generating replications within a replication, all of those individual samples within a replication, you have to consider to be dependent upon each other and not independent metrics of performance. You just can't take for granted that you've got independent metrics within a replication. And that's what we're sort of summarizing here. Now, what we can do is we can batch those replications together. And so if I run my sim for a very, very long period of time, and then I say the first 1,000 customers, what's their wait time? The next 1,000 customers, what's their average wait time? The next 1,000 customers, what's their average wait time? Those blocks, if they're large enough, are probably going to be uncorrelated from each other. And so in that case, we really can use each block as an independent replication of performance. So it's kind of like in a real system, if you make a change and you say, well, how long do I have to wait for me to see the effect of that change? Well, it might be that even though you immediately make the change, the performance you're seeing is still coupled to the performance from the old way. So if you did a change while the system's running, the people in line, they're still in line and they're still sort of feeling the effects of how it was before you added the extra cashier. But 100 customers down, then the effects of how the system was wash out. And now at that point, the performance that you're taking is independent from the previous performance. And you effectively can say, the data from 1 p.m. to 3 p.m., that's effectively a performance of testing cashier A. The performance from 3 p.m. to 5 p.m. is cashier B. And so we're going to compare those two together. An overlapping window mixes the two, and so we can't compare them. And that's what batching is as well. And so if we create large enough groups, we can turn one replication into many, but we have to have a very, very, very long simulation to do that. And so we're going to see examples of that with our steady state simulation, but I'm kind of suggesting that here is that sometimes you have autocorrelation, sometimes it looks like you don't, but maybe this autocorrelation, if I were to make each one of these batches larger, then maybe these numbers would start to be independent and you wouldn't just see a continuous rise. So if you need to run only one replication, but you want to generate multiple independent samples out of it, you have to make sure the replication is very long so you can cut it up into very large chunks that you then can take performance over. And that's something we're going to see in more general here. Then the other term that we need to be familiar with is estimator bias. So there is a real wait time in a population, and then there is a wait time we estimate in our sim. And hopefully, if we run our sim 10 times, sometimes it will be above the real wait time, sometimes it'll be below the real wait time. But on average, the simulated average will be dead on with the real system. If it happens to be that if we run our sims 10 times, and each one of those 10-point estimates actually clusters around a point that is greater than the real world system, then we say our simulation is biased. Our simulation overestimates the real world time. And that estimator bias is something that we want to try to remove. So that's what we're saying here, is that we can say that we've got, this is our estimator from our simulation. This is the real world average. This is a mean of the estimates from the sims. So we normally only run our sims once, but if you were to run them 10 times and take the average estimate, we're hoping that that estimate is pretty close to the real estimate. But if the average estimate across multiple runs of your sim significantly differs from the real estimate, our sim is adding bias. So that's what we mean by bias. It is an added portion to the real parameter that we're trying to estimate or subtracted. So questions about what I mean by bias would be an important term for our steady state simulations in particular. Okay, and then initialization bias, now that we talk about bias, this is bias introduced by, in a steady state simulation, by not discarding enough data or by starting the system out at a far away from steady state. So again, if the 24/7 grocery store normally has 3 people in line and you start your sim with nobody in line, then it takes time for the steady state queue length to go back up to 3. And that time where you're waiting for it to come back up to 3, those data are going to bias your queue lengths to be less than 3. So if you artificially start your sim to have empty queues when the real system never has empty queues, then then it's going to take time for your system to get close to the real system. And if you don't discard that data, you will underestimate the actual queue length. That's what an example of initialization bias. In a steady state sim, choosing poor initial conditions can bias your outputs by whatever those conditions are. And that's something we need to figure out how to reduce. And that's what we talk about in these units. So questions on what I mean by that? Yeah, initialization, absolutely. Because in a transient simulation, where you start is given to you. Like the bank will tell you every morning there's nobody in the bank until we open the doors. And so if it wouldn't make any sense to start the bank with 5 people in line. But in like a Walmart, you could say, oh, well, how many people should start in line? And Walmart says, what do you mean start? We're open all the time. So yes, absolutely. Great question. Initialization bias is a problem with steady state simulations. So that's what we're kind of saying here, that in our transient simulation, this, because we started the bank with nobody in line, the estimated average time in system. So let's say this is time in system. So initially, the first people to go into the bank at 8 a.m., they get out immediately, but everybody else has to wait, has people to wait from here. So you'd like to be these people, but you end up often being these people. Well, the average time in system is going to be the average from these people who wait in line and these people who didn't have to wait in line. So for the bank, this is a real average. That we trust that. We want to know that some people have the good experience, some people have the waiting experience. In the Walmart, nobody comes into the Walmart and doesn't have to wait in line because they're open 24/7 and there's always a line. But in the sim, it has to start somewhere. So if we started the sim with nobody in line, then we get the same rise here. But if we include these data up here, we're going to estimate the steady state wait time to be lower than it actually is because we're including these fictitious customers that didn't actually wait in line. So our job needs to be to truncate that. And that's one of the things that we talk about then in this unit is how we truncate that. All right. So that's enough. No clicker question today. Go vote if you haven't. And if you're taking 470, good luck. And we'll see you next time. Oh, let me stop the recording here.